Welcome to Module 15, Application Layer. This is the top of the OSIT CPIP stack. Everything students have learned about physical media, addressing, and transport now culminates in the actual applications people use every day: web browsing, email, file sharing. It's a very concrete, relatable module after the math-heavy stretch. Objective: explain how application layer protocols support end-user applications. Preview the topic table on screen. Application/presentation/session layers, peer-to-peer, web and email protocols, IP addressing services, DNS, DHCP, and file sharing services. This module covers a lot of named protocols: HTTP, SMTP, POP, IMAP, DNS, DHCP, FTP, SMB. The application layer is the closest layer to the end user in both OSI and TCP/IP models, the interface between the applications people actually use and the network underneath. Walk the protocol list on screen. HTTP, DNS, SMTP, POP, DHCP, FTP, IMAP, all living at this one layer, each covered individually later in the module. Presentation layer has three jobs, shown on screen: formatting data into a usable form, compressing it, and encrypting/decrypting it for transmission. Session layer creates and maintains the actual dialogue between applications, starting sessions, keeping them alive, and restarting ones that get disrupted or sit idle too long. Point out the format examples: video, MKV, MPG, KG, MOV, images, GIF, JPG, PNG, as concrete presentation layer work most students already recognize. TCP/IP application protocols specify the format and control info for common functions: web browsing, email, file transfer, name resolution. Critical requirement: both ends of a conversation must implement compatible protocols. A browser speaking HTTP needs a server speaking HTTP back. Most widely known examples on screen: HTTP, FTP, TFTP, IMAP, DNS, all get their own deeper coverage as the module progresses. In the client-server model, the client requests, the server responds, may also involve authentication and identifying exactly what's being requested. Data moving client to server is an upload. Server to client is a download. Classic example on screen: a home email client requesting unread mail from an ISP's mail server. In a P2P network, no dedicated server is required. Data comes directly from a peer device. Every connected peer can act as both client and server, with roles assigned per request rather than fixed. The diagram shows own computer serving files for one transaction, while simultaneously acting as a client for another. Roles aren't static, they flip based on what's being requested. A P2P application lets a device act as both client and server within the same communication. Every client is a server and vice versa. Each device needs both a user interface and a background service running. Worth noting: some P2P apps use a hybrid model where sharing itself stays decentralized, but an index of where resources live sits on a centralized directory server each peer checks. Common P2P networks named on screen: BitTorrent, Direct Connect, eDonkey, Freenet, many built on the Gnutella protocol, where users share entire files with each other. Gnutella-compatible clients include Torrent, BitComet, DC++, Deluge, eMule. These let users connect, locate, and access resources shared by other peers on the network. Walk the full four-step process of loading a web page, shown on screen. Type the URL, user enters the FQDN, resolve the name, browser asks DNS to convert the name to an IP, send the request, browser sends an HTTP GET to that IP, receive the response, server sends back HTML, browser renders it. This whole sequence, combining DNS and HTTP, happens before a single pixel of the page shows up, and every subsequent slide in this section digs into one of these pieces. HTTP is request/response. The client sends a request, and HTTP defines exactly what kind. Three request types shown on screen: GET, asking for data like an HTML page; POST, uploading data like a form submission; and PUT, uploading a resource like an image file. Walk the sample GET request format on screen. This is literally what a browser sends behind the scenes for every page load. HTTP isn't secure. Requests and responses travel in plain text, easily intercepted and read. HTTPS solves this with authentication and encryption, while following the exact same request/response process underneath. The actual encryption comes from TLS, or its predecessor SSL, wrapping the data stream before it touches the network. Same HTTP process, just wrapped in encryption. Email is a store and forward system. Messages sit in databases on mail servers, and email clients never talk directly to each other, always going through a server. Sending uses SMTP. Retrieving uses either POP or IMAP. Each of those three protocols gets its own dedicated slide next. SMTP is what actually sends email, both client-to-server and server-to-server across the internet. Every SMTP message needs two parts: a properly formatted header, sender/recipient addresses, and a body, any amount of text. Important limitation to stress: SMTP only sends. Retrieving mail is a completely separate job for POP or IMAP. POP retrieves mail by downloading it to the client and then deleting it from the server by default. The server listens passively on TCP port 110. Since mail gets removed after download, there's no centralized backup, which isn't ideal for a business needing one. POP3 is the version in common use today. IMAP retrieves mail differently. It downloads copies while the originals stay on the server until manually deleted, and users can build a folder hierarchy on the server that the client mirrors. Key sync behavior: delete a message on the client, and IMAP synchronizes that deletion back to the server, keeping both copies consistent, unlike POP's one-way download and remove. Numeric IP addresses are how devices actually communicate, but they're miserable for humans to remember. Domain names solve that. A fully qualified domain name like www.cisco.com is far easier to remember than 198.133.219.25. And if the underlying numeric address changes, it's completely transparent to users since the domain name stays the same. DNS is the automated service matching names to addresses. DNS servers store several resource record types shown in the table: A IPv4 address, quadruple A IPv6 address, pronounced quad A, NS, authoritative name server, MX, mail exchange record. If a server can't resolve a name itself, it queries other servers and caches the result temporarily. Windows caches resolve names too, viewable with ipconfig/display DNS. DNS uses a hierarchical system broken into manageable zones. Each server only manages its own zone, forwarding requests outside that zone elsewhere. This hierarchy is exactly what makes DNS scalable, spreading resolution work across many servers instead of centralizing it. Walk the tree diagram on screen. Root, then TLDs like .com/.net/.edu, then second-level domains like cisco.com, then specific hosts like www.cisco.com. nslookup lets you manually query name servers from the command line, genuinely useful for troubleshooting resolution issues or confirming a name server status. Walk the sample session on screen, querying cisco.netacad.net and getting back its resolved IP address, exactly what a browser does automatically behind the scenes. DHCP automates assigning IP addresses, subnet masks, gateways, and other parameters, called dynamic addressing, contrasted with static addressing, where an admin manually configures every host. When a host connects, it requests an address, and the server leases one from a configured pool for a set period. DHCP shines on larger or frequently changing networks. Home routers usually serve this role for home networks. The DORA process. 4 messages establish a lease, shown on screen. Discover. Client broadcasts looking for any DHCP server. Offer. Server replies with an offered IP, mask, DNS, gateway, and lease duration. Request. Client requests the specific offer it wants in case multiple servers replied. ACK. Server acknowledges, finalizing the lease. This sequence is worth having students memorize by name. DORA. If multiple DHCP servers respond, the client's request message specifies exactly which offer it's accepting. The client can even request a previously held address. If still available, the server sends ACK. If not, it sends NAC and the whole process restarts with a fresh discover. Leases must be renewed before expiring via another request. Mention DHCP v6 uses an analogous message set: solicit, advertise, information request, reply. FTP was built specifically for client-server data transfer. An FTP client is just an application used to push, upload, and pull download data with an FTP server. This is the exact same client-server upload/download relationship introduced back at the start of the module, now with FTP as the concrete protocol implementing it. SMB is a client/server file-sharing protocol describing the structure of shared resources, directories, files, printers, serial ports. It's request response, with a common message format across all types. 3 functions shown on screen: session control, start/authenticate/terminate, resource access, control file and printer access, and messaging. Let one application send/receive messages to another device. Unlike FTP, SMB clients establish a long-term connection. Once connected, server resources behave as if they were local to the client. Since Windows 2000, SMB runs directly over TCP/IP using DNS naming, rather than older non-TCP/IP methods. Worth mentioning, Linux/Unix systems use Samba, an SMB implementation, to interoperate with Microsoft networks, and macOS supports SMB sharing too. Close the module walking each bullet: the application/presentation/session layer roles, client-server versus peer-to-peer, HTTP's GET/POST PUT, and HTTPS's TLS/SSL wrapper. Email always routing through servers with SMTP sending and POP IMAP retrieving differently. DNS's scalable hierarchy resolving names to addresses. DHCP's DORA process automating address assignment, and FTP versus SMB's different approaches to file sharing.